This is the second part of the AMC12A 2019 solutions for the problems 10 through 15. In this video, we're going to be covering the solutions to problems 13 to 15. And in the last video, which you can check out if you didn't see, I went over the solutions to problems 10 through 12. 13, it's a counting problem, and it reads, how many ways are there to paint each of the integers 2 through 9, either red, green, or blue, such that each number has a different color from each of its proper divisors? So let's start by considering the numbers 5 and 7. These are the only numbers between 2 through 9 that don't have any divisors and also don't have any multiples. So these numbers can be painted any color, and it doesn't matter. So there's 3 choices for 5, and there's 3 choices for 7. So let's consider the number 2. 2 has the multiples 4, 6, and 8, right? So we have 2, 4, 6, 8. So basically 2 can't be the same color as 4. 4 can't be the same color as 8, and 6 has to be either the color of 4 or the color of 8, since it's also a multiple of 2. Right? So 2, we have 3 choices for 2, right? And then after that, we have 2 choices for 4 and 1 choice for 8. And 6 would just be either the color of 4 or the color of 8. So it's another 2. So after this, we're left with 3 and 9. So 3 is a divisor of 6. So we're also left with 2 choices for 3, and 9 just doesn't have to be the same. Just doesn't need to be the same color as 3. So there's also 2 choices for 9. So here we have 3 times 3 times 3 is 27 times the 4 2's, which is 16. And this should come out to 432, which is E. 14, it reads, for a certain complex number C, the polynomial p of x has exactly 4 distinct roots. So in this problem, we know that the roots of x squared minus 2x plus 2 and the roots of x squared minus 4x plus 8 all have to be roots of p of x, since if either of these equations is 0, then p of x is also 0. So let's find the roots. For x squared minus 2x plus 2, we set this equal to 0 and do the quadratic formula. We find negative b plus or minus square root of b squared minus 4ac, 4 times 2, over 2a is going to be equal to, looks like 2 plus or minus, well, 2i over 2. So this is going to be equal to 1 plus or minus I. So for this one, we have x squared minus 4x plus 8 equals 0. So x is going to have to be 4 plus or minus the square root of 16 minus 4 times 8 over 2. This is 2 plus or minus, 4 times 8 is 32, 16 minus 32 is negative 16, so 4i over 2. So this is 2 plus or minus 2i. So we notice that since the polynomial has 4 distinct roots, all these roots are here. So the roots are 1 plus I, 1 minus I, 2 plus 2i, and 2 minus 2i. So basically, this expression right here has to share the same roots. So the 2 roots have to be a combination of the 4 roots that I just said. What we need to take into account is that the constant terms multiply to 4, and also that the I is cancelled. So also we need to take into account that we have to take one term from here and one term from here, since if we just use 2 plus 2i times 2 minus 2i, we will get 8 as the constant term. And if we use 1 plus I times 1 minus I, then we'll get 2 as the constant term. If we want 4, we need to take 1 from here and 1 from here. Also, like I mentioned, the i's cancel, so we can't have something like 1 plus I times 2 plus 2I, or we can't have something like 1 minus I times 2 minus 2I. That way we'll have the I still remaining. So basically the only two possibilities we can have is 1 plus I times 2 minus 2I, or we can have 1 minus I times 2 plus 2I. So this, sorry, that was really bad. This is equal to 2, the i's cancel, so we're left with 2 plus 2 is 4. And here we also have the i's canceling because we have 2 times negative I and 1 times positive 2I. So here we also have 2 plus 2, which is 4. So for both of these instances, we have the constant term of 4. So now all we have to do is find what C is. So to find C, we know by Vietas that C is going to be the sum of the roots, right? So in order to take the sum of the roots, we add 1 plus I to 2 minus 2I. This is equal to 3 minus I. And with this equation, we have 1 minus I plus 2 plus 2I, which is going to be 3 plus I. You might be asking, if you have a complex number, what does the absolute value of that complex number mean? Well, this means that if you put this on the complex plane, the absolute value of C is going to be the distance between the origin and that point on the complex plane. So basically, for both of these points, if we with a complex plane, this 3 minus I is gonna correspond to 3 negative 1 on the traditional Cartesian plane, and 3 plus I is gonna be 3 comma 1. And these points are both square root of 10 units away from the origin, since by the Pythagorean theorem, if this is 3 and this is 1, this is going to be square root of 10, right? So the answer is going to be number 15. Asks, positive real numbers a and b have the property that the square root of log a plus the square root of log b plus log square root of a plus log square root of b equals 100. And all four terms on the left are positive integers, where log denotes the base 10 algorithm. What is ab? So the first thing we need to know in this problem is the form of a and the form of b. So since the square root of log a is a positive integer, a has to be in the form 10 to the, well, let's call it x squared, where x is also a positive integer. Why? Because if we take the log of this number, we're going to end up with x squared, and that still has to be a perfect square. So a has to be in this form, and b has to be in a similar form, right? So let's call b 10 to the y squared. As for log squared of a and log squared of b, we can also use this form, since if we plug 10 to the x squared into a, we're going to end up with equal to 10 to the x squared over 2. And taking the log of that, we have x squared over 2. Similarly, with log of the square root of b, we have y squared over 2. So to rewrite this equation, we can write x plus y plus x squared over 2 plus y squared over 2 equals 100. After that, we can multiply 2 on both sides to get 2x plus 2y plus x squared plus y squared is 200. So where do we go from here? Let's group the x's together and group the y's together and see if we can get anything done. So here we can make the realization that this is equal to, well, if we add 1 here and add 1 here, we can write it as x plus 1 squared plus y plus 1 squared is equal to 202. And from here, we can just try sums of squares that add up to 202. There aren't that many. And there's actually just one, which is 11 squared plus 9 squared, I think. This is 121, this is 81, and this is these add to 202. So that means that x is 11, y is 9, x plus 1 is 11, and y plus 1 is 9. Or the other way around, it doesn't really matter. But anyway, we can just say one of them is 10, one of them is 8, and AB is, and we have to plug them back in, obviously. So we have A equals 10 to the 100, and B equals 10 to the 64. If we multiply these two together, you just add the exponents, and you have 10 to the 164, which is D. That helps you with understanding the solutions to the 2019 AMC12A. And make sure to leave a like and subscribe if you liked it. And I'll come out with a new video every single Friday. So make sure to turn on notifications to receive a notification every time I post a video. Thank you, and bye.